Okay, so we're moving into anti-differentiation, which is sort of the reverse of what we've been doing. Some of these questions are a little bit rhetorical, like I'll just answer the question for you. But so first let's think about how we would describe to find the derivative of a polynomial type function. So there's kind of two steps. The first step, and what we're really talking about here is power rule, right? So the first step would be to multiply the exponent of each term by the coefficient of that term. Actually, I'm going to say it the other way. Sorry, reverse. We're going to say that we multiply the coefficient of each term by the exponent of each term, or of that term. Step 2 would be to decrease the exponent of each term. Oops, forgot the R. Each term by 1. That's our power rule, right? So to do the antiderivative, or the reverse of that, we're going to do the opposite thing in reverse order. So step 1 will actually be to increase the power of each term. We'll just think one term at a time. Increase the power. And then divide the coefficient, I'll say of each term, but we're really just doing this one term at a time, by the new exponent. So the antiderivative of a function f is denoted by the notation, okay, given here. So when you're finding the antiderivative of a function, you're finding the function of which f of x is the first derivative. So you're finding the function for which this is the answer. This part here, the little squiggly symbol and the dx, that's notation. The function, which we call the integrand, that's the meat of the thing. That's the function there that you're trying to find out. What was the function that's the derivative of? So then we can kind of find f. So let's take a look at the way they write it here. So what they write is the integral of f prime of x. So in this case, we've got the notation f prime. So then f of x is now, that's the function that was the original function. Now we've taken the derivative of it. So we're saying we're kind of going backwards here. So the problem is that what we come across right away is it could have been f of x plus 7. It could have been f of x minus 8. It could be f of x plus any constant. So we're going to call, hold on, I got to. All right, so it could be any constant. We're going to call that constant the constant of integration. There's no way of knowing what it was. Do you agree that the derivative of all of these functions here all have the same derivative, f prime of x? So the integral of f prime of x could have been any one of these functions. So we have to keep track of it. We say that it's going to be plus c. So if I were to write this a little better to make a rule, the integral of f prime of x dx is equal to f of x plus c. Meaning that could be any constant. This symbol is called an integral. It means the verb to integrate. Well, actually, we're not going to talk about that. It's to take the antiderivative. This is the variable of integration. These two things, the integral and the variable of integration, are notation. They're important. They mean stuff. We'll get into what they mean a little bit later when we do some applications. There's a little more meaning there than just that it's notation. But what I want to tell you is whenever you have an integral, you have to have a variable of integration, or with respect to whatever variable we're using. So that's like a dx means we're taking the integral with respect to x. So what happens is sometimes students will write the integral symbol and forget the dx, or vice versa. Those two things stay together. Whenever you have an integral, you have an integral symbol, you have a variable of integration. You can't have one without the other. And when you actually do the integration, they go away. I think of it like this. If I ask students sometimes in algebra to do the square root of 25, they'll write this. They'll write square root of 5. So this symbol means something, and when you perform that operation, the symbol goes away. So it should just be 5. Same thing is going to happen here. When we integrate the function, the symbols go away. Don't write them in your answer. All right, so let's take a look here. Now remember, if we're thinking about going in reverse, the question here is, what was the original function whose derivative is this function here, just the integrand part? This is notation saying take the integral. That's also notation that they always belong together. So if we increase the power by 1, and then divide the coefficient by that new power, this is what we get, and we do it for each term. So the x becomes x squared, and we divide our coefficient by the new power, and then this guy becomes 3x. Because this is really 3, if I write this on the side, you can think of it as x to the 0. So if I increase its power by 1, it's going to be a power of 1, and then if we divide by 1, it doesn't change anything. So what we end up knowing is the integral of a constant, of any constant, with respect to x, is going to be equal to cx, right? Because remember, this is the derivative of some function, so 3x, the derivative of 3x will always be a constant. So whenever you have a constant, the original must have been just an x to the first. So what I kind of say is we just kind of put an x on those constants when we integrate them. And then we always have to account for some unknown constant of integration. So if we simplify this thing, all right, moving along. So this guy already is not in the proper form to do power rule. So I have to do some simplification first, some algebra simplification. So if I distribute this division, I arrive at this polynomial. I still have the problem with 4 over x. So now we're going to call that negative 4x to the negative 1. We're going to bring it up. This is my integrand, so I'm applying power rule to that. So if I apply power rule, I'm going to get x to the third, and then it's going to be 1/3. This is a constant 2, so its integral must have been 2x. Okay. Oh, and by the way, you could always just take the derivative of your answer and see if you got it right. So I kind of do that here as I'm going. Like if I did the derivative of what I have so far, I can see that I'm doing good. I'll get the right answer. Now if we increase this power by 1, we get 0, or the power of 0. And then if we divide negative 4 by 0, I don't really want to divide the x by that. We run into a problem, divide by 0. That's an undefined number. So this, when we're trying to apply power rule and integration, if we run into this problem, that's because something's going on here. There's something else. So when you try to divide by 0, that should set off an alarm bell in your head, like, wait a second, we can't do that. So let's look at this 4 over x, the integral of that, on its own. We have to make a rule for that when it's over x to the first. Remember, we're looking for some function where the derivative of it would have been this. And that function is going to be, because the derivative of ln of x is 1 over x. So this is not a power rule for integration, right? So we call this, when we increase the power by 1, divide by the new power, that's power rule for integration. It breaks when we have a power of 1 in the denominator, right? Because we bring it up, it's a negative 1, the whole divide by 0 part breaks it. And that should remind us like, oh wait, because the derivative of ln of x is what gives us 1 over x. It's not a power rule law. This is a fact recall. We know that the derivative of ln of x, okay, ln of x equals 1 over x. So we're going to use that in reverse. So we know that if I had this function, negative 4 comes along for the ride, the derivative of ln of x is 1 over x, so that's negative 4 over x. So we know that this turns into negative 4 ln of x. Then we have plus c for that unknown constant of integration. So I'm showing you like power rule essentially for integration, but there are some tricks we come across, and this is the first problem. What if it's divided by x? That's because it's not power rule at all. It's a natural log function. So we need to make a little rule that we can remember for that. So anytime we're trying to integrate a constant over x, the integral of that is going to be the constant times the ln of x plus c. And let's not put that plus c in there for now. We know that there's a constant of integration, right? But I don't want to confuse it with that c. I probably should have used a k, but so anytime we have the integral of c over x to the power of 1, if it's not a power of 1, we're okay. Like if it's a power of 2, we can still apply power rule. It's just that over power of 1 where we get the natural log. All right, so let's look at another one. How do we deal with this? There is no product rule for integration that we know of right now. So we just have power rule, so we're going to multiply it out. We're going to do some work first. So it's going to be 2x squared minus 3x plus 4x minus 6. So we're going to get the integral of 2x squared plus x minus 6. And now we can apply power rule here, so it becomes x to the third, and it's 2/3 plus x squared, so it's 1/2 minus 6x plus our constant of integration. All right, and that's our answer. And again, we don't know what that c is. We're just accounting for it. We don't know exactly what it is. Okay, we cannot have x in the denominator, so I've already told you that. We want to bring it up like we did here. But instead, except in this case, when it's negative 1 power, we know that that's actually going to be the natural log. If it's any other power, we're okay. We can do power rule. So let's take a look at this one. If we bring our x to the 1/2 power up, then we can apply power rule. If I add 1 onto it, so that's what I usually do to show I'm adding 1 onto it, I get x to the 1/2 power. Now the new power is 1/2, so whenever the power is a fraction or the coefficient is a fraction, instead of dividing by the new power, I multiply by its reciprocal. It just goes, it's more easy. It's cutting out a step. Because look, if I divide by a fraction, I'm going to end up multiplying by its reciprocal anyway. So whenever either one of these numbers, the coefficient or the power, is a fraction, or both, I end up, instead of dividing by the power, I multiply by its reciprocal. So we end up getting 4x to the 1/2. So we end up getting 4 root x plus our constant of integration. I always put that constant of integration in at the last step. Okay, so that's how you do some polynomial type 1s. The only snag we run into is this guy. Got to watch out for natural log. And when will you know to do that? Anytime you find yourself applying power rule and you're trying to divide by 0, you should say, oh, wait a second. Yeah, that's because that's a natural log, the integral. Now we're going to look back at some other derivatives we knew. We knew this derivative, so now we know an integral. We know that going in the other direction, that the integral of cosine of x is sine of x plus our constant of integration. And since we know the derivative of cosine is negative sine, we know the integral of negative sine is cosine, but we're going to just memorize the rule for what the integral of sine is. That means it's going to be negative cosine plus our constant of integration. Okay? So whatever rules you remember for derivative, now it's backwards in terms of negative signs, right? So when you did the derivative of cosine, that's when you had to switch the sign. Now it's when you do the integral of sine that you have to switch to a negative sign. So we'll just figure that out in practice. So technically, I'll show you some stuff here. we can do this in parts, or we can do it one term at a time. So technically I'm supposed to kind of write these as two separate integrals because we only have a rule for sine and cosine, right? That's it. That's the only rule we have. So then what do we do with this 2? Well, the 2 can be pulled through the integral just like we can pull it through differentiation. Remember, if we were doing like the derivative of 4 times f of x, we could say it's 4 times the derivative of f of x. So I can pull the 4 out through the differentiation. We can do the same thing with integration. And we don't always do it with derivatives, but we have to understand that it's a property. So same thing here. This is a property. I can pull the 2 out. I can break up the integration into term by term. And now I could actually integrate these because I have a rule for the integral of sine. 2 comes along for the ride. The integral of sine is negative, so I'll put it in parentheses because it's multiplication, is negative cosine. And then the integral of cosine is sine. So then I'm going to get this 2 times negative cosine is negative 2 cosine of x plus sine of x plus c. The question becomes, do you have to show me all these steps with pulling the 2 out and separating and rewriting each integral for each term? You don't have to. You could jump straight from here to here if it makes sense for you, if you understand what's happening, right? 2 comes along for the ride. The integral of sine is negative cosine. The integral of cosine is sine. All right, let's try this guy. We go one term at a time. The first term is power rule, so it's t to the third, and then divide by that new power. And then the integral of sine is negative cosine, so it was already negative, so it becomes a positive. And we have plus our constant of integration. On this guy, we've got 2 terms again. We've got power rule on the first one, so it's x to the second power, and then I take the 4 and I divide by the new power 2. The negative 3 comes along for the ride. The integral of cosine is going to be sine. So then if I simplify, I got 2x squared minus 3 sine of x plus our constant of integration. I always do that on the last step. I don't add the constant as we go. Here's another one with multiple terms. This is really x to the 1/2. So you could require a rewrite if you like. So if I increase the power by 1, when it's fractions, I like to show that. That's helpful to write that 2/2 or whatever. So I end up getting x to the 3/2. And now it's going to be, instead of 1 divided by 3/2, it's going to be 1 times 2/3. And then the integral of sine is negative cosine. And then plus c, a constant of integration. Sorry, I'm still getting over sickness. All right, so now we have some given information about the derivative and the second derivative to find our f of x. So let's see what we can do here to figure out what our original f of x is. So what we do here is we start with our second derivative. And we're going to work all the way back to find f of x, right? So if our second derivative is 2, that means the integral of 2 with respect to x, okay? Because we know that this is an x here. The second derivative is 2 with respect to x. If we do that integral, we should get our first derivative because we're going kind of backwards. So the integral of 2 is 2x, but then we have plus c, plus the constant of integration. And that is now going to be our first derivative, right? Let me buy myself some room here. So I just integrated our second derivative, and I got f prime of x equals that. Now, these conditions allow us to figure out what c is. They give us a set of numbers that can pinpoint exactly what c has to be. So I use those conditions. I say, well, if I plug in 2 for x, I should get 5 in my first derivative. So now I get 4 plus c equals 5. So I'm going to subtract 4, c equals 1. So now I just found my c. You can do that if they give you conditions, meaning if they tell you a value for x for which you know the first derivative. So then f prime of x is now 2x plus 1. Now I can find f by integrating that with respect to x. So I do power rule on that guy. I get x squared, and then it's 2 divided by the new power 2 plus x. And that's going to be f of x plus our constant of integration. Now they give us conditions for f. They say when I plug 2 into f, I get 10. So f of 2 equals 2 squared plus 2. I just simplified that to a 1, by the way. 2 squared plus 2 plus c. That's going to be equal to 10, right? So we get 4 plus 2 plus c. 10 equals 6 plus c. C equals 4. So we now know that f of x is x squared plus x plus 4. Because they give us these conditions along the way, what they tell us what f prime of 2 is equal to and what f of 2 is equal to, we can find out what the function f is. So again, they start us off with the second derivative here as a function. Notice it's a function of x. Then they give us some conditions along the way that we can use to calculate our c's. If you take any physics, this is sort of like when you're having to find initial height, initial position, initial velocity, as you're working through taking the derivatives of each of the functions there, the position, velocity, acceleration. Same idea. All right, so if I start with the second derivative as x to the negative 3/2, that means if I integrate that with respect to x, I will get my first derivative. So we're going to apply power rule on this guy. So I'm going to add 1 to the exponent. So I get negative 1/2. Then times the reciprocal of that, so it's a negative 2 plus c. So that's my f prime of x. So my f prime of 4 is equal to negative 2 over x. So that's a 4 because we're plugging in 4 plus c, which equals 2. Right? So let's simplify this guy. We get a negative 1 plus c equals 2. So then we get a c equals 3. So then my first derivative is now negative 2 over root x plus 3. So then we want to keep going to get to f. So if we integrate that, negative 2 over root x plus 3 with respect to x, I can do power rule again. This requires a bit of a rewrite. We'll call it x to the negative 1/2 plus 3 dx. So now if I apply power rule, I get x to the 1/2. I'm multiplying by the reciprocal, so I get a negative 4 plus 3x plus c. That is f of x. To figure out what the c is, I know that f of 0 equals 0. So if I plug a 0 in, I get equals 0. So we get c equals 0. So in this case, c is 0. So f of x, we know what the constant is. It's 0. So we've got negative 4 root x plus 3x plus 0. So let's look at an application problem here. Okay, so we're talking about an evergreen nursery usually sells a certain shrub. After 6 years of growth and shaping, the growth rate during those 6 years is approximated by the differential equation. So here's where we're hearing this word, I think, for the first time, differential equation. It means it's an equation that is the derivative of something. So that's a differential equation. We can tell by the dh over dt that it's a rate, right? It's a rate of change of height with respect to time. All right, so that's sort of like they're giving us the derivative of height. So there is some height function. They've taken the derivative, and now they have the rate of change of the height. Where t is the time in years and h is the height in centimeters, The seedlings are 12 centimeters tall when planted at time equals 0. They're giving us what we would call initial conditions. So for the height function, which we don't have yet, if you plugged in 0, no time has passed, you would get 12 centimeters, right? That's the initial condition. So if we do have to find our height function from our differential equation, we now can find out what the constant of integration is, like we did up here, because we have some type of condition that I can plug in to solve for C. That's why they have to give you that condition. All right, so the first question says, find the value of the differential equation above when t equals 3. So dh dt equals 1.5 times 3 plus 5. So that's going to be 9.5 centimeters per year. Remember, it's a differential, so it's a rate that we're finding. So using correct units, explain what this value represents in context of the problem. It means 3 years after planting, the height of the shrub is increasing, because it's a positive rate, at 9.5 centimeters per year. So it doesn't tell us the height of the shrub at all. It just tells us how fast it's growing. Now they want us to find an equation for height. So now we take our differential, and we integrate both sides, because we want to get backwards to find what function is this the derivative of. So here's where this notation dh over dt comes in handy. We can treat it like division, so we can multiply both sides by dt. This step is called separation of variables when solving a differential equation. Notice that now on one side of my differential equation I have all one variable, and on the other side I have all the other variable. So now, just like when you do any operation, you have to do it to both sides. So I'm going to take the integral of both sides here. And notice now I need the integral here. I need that dt because I have an integral symbol. So this is now my integrand. And over here, I have an integral and a symbol, and there is no integrand, so I'm going to rewrite this and show you what it would be. If there's nothing there, it's like a 1, because 1 times dh is dh. So if I integrate 1, that's just going to be x, but in this case, they tell me the variable is h, so it's going to be h. The integral of 1 is h. Think backwards. What's the derivative of h? It's 1. Okay, so that's why the variable of integration is important. Right here you could see I had a constant only when I integrated. What variable do I call it? Well, the variable of integration is telling us what it is. Here I already have a t in there, so I know what the variable is. I apply power rule, it becomes t squared, and then I have 1.5 divided by 2, then plus 5t, and then we have our plus c. So our height function, with respect to time, I can write it in function notation if I like, is now 0.75 t squared plus 5t plus c. Now, using my initial conditions, it says we want to, for any year t, then determine how tall the shrubs are when they are sold. So now we want to use our initial condition to find out what c is, so then we can use this equation to find the height of a certain shrub. So the initial conditions were as h of 0 equals 12. So if I plug in 0 for t, I end up getting c equals 12, right? Because I get 0.75 times 0 squared plus 5 times 0 plus c equals 12. So that's c equals 12. So my new height function for these shrubs, I now have the function that tells me the height, not just the rate of change of height, is 3/4 t squared plus 5t plus 12. Right, so that's my height function. Given any year, it'll tell me the height of the shrub. This equation, given any year, would tell me the rate of change of the height of the shrub. So, what was the question? Then determine how tall the shrubs are when they are sold. So they're sold when? After 6 years. So if we put 6 in, they are 69 centimeters tall. All right, so let's look at our last one here. Is this? Yeah, that's the last one. Particle moving. So we're back to particle motion here. They tell us at time 1 position is 4. So they give us a velocity function. They do give us information about the position function. At time 1, the position is 4. Those are conditions, again, that will allow us to find or solve for our constant of integration. So what's the acceleration of the particle when t equals 9? Well, we know that the velocity function is t to the negative 1/2. So the acceleration function is the derivative of that. So I do derivative. Don't forget your power rule for derivative now. If I subtract 2 over 2, I get negative 3/2. So I get a of 9 equals negative 1 over 2 times 9 to the 3/2. So 9 to the 3/2 is, well, 9. The square root of 9 is 3. Then 3 cubed is what? 27. So it becomes negative 1 over 2 times 27, negative 1 over 54. That would be the acceleration of the particle when t equals 9. What's the position of the particle when t equals 9? Well, we've got our velocity function. And we know that velocity is the derivative of position. So now we want to integrate this function with respect to t to get our position function. I should use p for position. That's what I used earlier. Right up there? Yeah. All right, so our position function is going to be the integral of our velocity function with respect to time. So our position function is equal to power rule. I get t to the 1/2, and then it's times 2 plus c. So my position function is 2 root t plus c. And now I can use those conditions they gave me. P of 1 equals 4. So P of 1 equals 4. So I get 2 plus c equals 4. C equals 2. So now I know that my position function is 2 root t plus 2. And now they want to know what's the position of the particle when t equals 9. So I plug 9 into my position function. I get 8. That's anti-differentiation.